Chapter 7: Quantum Theory and Atomic Structure. In this chapter, we're going to study the quantum mechanical model of the atom. We'll start with the nature of light, and I'm going to show you light is a wave but also have particle properties called wave-particle duality. In fact, not only light, but atoms, electrons, molecules, they all have wave-particle duality. You may already know that light is part of electromagnetic radiation. Electromagnetic radiation is a wave that is described by the following variables and constant: frequency, wavelength, speed, and amplitude. Water wave, for example, is a traveling wave. The highest point is called a crest, and the lowest trough. Amplitude is the height of a wave crest or depth of a trough. Wavelength is the distance between two adjacent crests, which is considered the distance of a wave travels in one cycle. The speed of a wave is the distance it moves per unit time, which is meters per second. Frequency is defined as how many cycles a traveling wave travels per second. Wavelength is the distance a wave travels in one cycle. So the product of these two, the frequency times wavelength, gives you how long a wave travels in 1 second, and that is the speed. Note that the most commonly used symbol for frequency is F, but in this case we use a Greek symbol nu. This symbol is similar to the symbol we used for speed, V. Speed of light is represented by symbol c. So c equals frequency times wavelength. It turns out that the speed of light is a constant, which is 3 × 10⁸ meter per second. The left side shows 3 different colors of light: red, yellow, and blue. Red light has the longest wavelength, and blue light has the shortest wavelength. Yellow light is in between. Since they all have the same speed, so longer wavelength means smaller frequency. Suppose red light travels 2 cycles per second, so the frequency is 2. And with the same speed, yellow light would travel 4 cycles, so frequency is 4. And for blue light, it will be 8. So wavelength, frequency, they are inversely proportional. The color of light depends on its frequency and wavelength. What about amplitude? The amplitude of light determines its brightness and intensity. Just like water wave, a strong water wave has a high amplitude. A light with a higher amplitude is more intense and brighter than a light with lower amplitude. This diagram illustrates the electromagnetic spectrum, and the visible light is only a small part of it. Note that wavelength, frequency are inversely proportional. So to the left side, frequency increase, but wavelength decrease. Gamma ray has the highest frequency, but the lowest wavelength. And the next one will be X-ray. And then UV, visible, infrared, microwave, radio wave. Radio wave have lowest frequency but largest wavelength. Later we'll show you that the energy of light is proportional to the frequency, and therefore gamma ray has the highest energy, and the next will be X-ray, and then UV, visible, infrared, and the radio wave has the lowest energy. And in the visible range, blue light has the higher frequency than yellow light, and then higher than the red light. So blue light has higher energy, and then the yellow light, and then the red light is the lowest energy. Sample problem 7.1. A dental hygienist used X-ray with wavelength 0.5 angstrom to take a series of dental radiographs while the patient listens to a radio station with wavelength 325 cm and looks out the window at the blue sky with wavelength 473 nanometer. What is the frequency in per second of the electromagnetic radiation from each source? To calculate the frequency, we use the equation speed of light equals wavelength times frequency. So frequency should be speed of light divided by wavelength. Now speed of light is a constant, which is 3 times 10 to the 8th power, and the unit is meter per second. So the wavelength must also in meter. And the first step, we need to convert angstrom, centimeter, and nanometer to meter, and then plug in this equation to calculate the frequency. So for X-ray, the wavelength 0.5 angstrom, 1 angstrom is 10 to the negative 10 meter. So using this as a conversion factor, we cancel angstrom, will give you meter. So the answer is 5 times 10 to the negative 11 meter. And then we plug in the equation speed of light divided by wavelength, and that gives you 6 times 10 to the 18th power per second. So for radio signal, the wavelength is 325 centimeter. 1 centimeter equals 10 to the negative 2 meter. As using this as a conversion factor, cancel centimeter, give you meter, and then use the speed of light divided by wavelength, give you 9.23 times 10 to the 7th power per second. For the blue sky, the wavelength is 473 nanometer. 1 nanometer equals 10 to the negative 9 meter. So using this as a conversion factor, cancel nanometer, give you meter. And then speed of light divided by this wavelength, give you 6.34 times 10 to the 14th power per second. You have learned that light is a wave, but how do you know that? Well, first, let's look at the differences between a wave and a particle. A wave travels at different speeds through different media, and this difference causes the change in direction, and this is called a refraction. If light strikes the boundary between the air and water, it changes direction and continues at different angle. On the other hand, if you throw a pebble through the air into a pond, it continues to slow down gradually along a curved path after entering the water. And this is not refraction. Particles such as pebbles do not undergo refraction, but light does. When a wave strikes the edge of an object, it bends around it in a phenomenon called diffraction. Here shows a plane wave. The red lines represent crests. Let's take water wave as an example. If you look from top to bottom, you see lines of crests. If the wave is blocked with a small opening, the wave will bend around both edges of the slit and forms a semicircular wave on the other side of the opening. In contrast, when you throw a collection of sand at a small opening, some particles hit the edge while others go through the opening and continue in a narrow group. Particles do not undergo diffraction, but a wave does. We just showed the diffraction, which happens when a wave passes through one slit. If a wave passes through two adjacent slits, the adjacent circular waves interact in a process called interference. If the crests of the wave occur inside, Okay, so like here. So they interfere constructively. The amplitude added together to form, for water, it forms highest point. For a light wave, it forms the brighter region. If crests coincide with troughs, which is out of phase, they interfere destructively. The amplitude cancel. For water wave, it forms the lowest point. For light wave, it forms a darker region. This diffraction pattern clearly shows light is a wave. We all know that when an object is heated to a high temperature, it emits visible light. In fact, all objects emit light, and this is related to so-called blackbody radiation. We also know that the color of the emitted light is related to the temperature of the object. If you heat an object to high temperature, it may emit red light, but if temperature goes to even higher, the color may change to blue. Since color is related to wavelength and frequency, and temperature is related to energy, so energy is therefore related to frequency and wavelength. Scientists try to find a mathematical equation to correlate the energy given off by a hot object and the wavelength of the emitted radiation, but most of them failed. Until 1900, a German physicist, Max Planck, proposed the following equation. Energy is proportional to frequency times a constant h, which we nowadays call Planck constant. And the value is about 6.63 times 10 to the negative 34 joule second. And it also multiplies a constant, or not constant, is a positive number, n. N is a positive integer. It can be 1 or 2 or 3 and so on. So the possible energy can be h times nu, or 2 times h nu, 3 times h nu, 4 times h nu, and so on. Since the hot object emits only certain quantities of energy, and that energy must be emitted by objects' atoms, this means that each atom emits only certain quantities of energy. It follows then that each atom has only certain quantities of energy, and therefore the energy of an atom is quantized, which means that it occurs in fixed quantity rather than being continuous. Each fixed quantity of energy is called a quantum, which is just h times nu, and the plural of quantum is quanta. An atom changes its energy state by emitting or absorbing one or more quantum of energy, and the energy of the emitted radiation is equal to the difference in the atom's energy state, and therefore delta E equals delta N times h nu. The smallest change occurs when an atom in a given energy state changes to an adjacent state, and that means delta N equals 1. So delta E equals h times nu. We all know that speed of light equals wavelength times frequency. So frequency is the speed of light divided by wavelength. So plug in here, we get delta E equals Planck constant times speed of light divided by wavelength. And that indicates that energy is proportional to frequency, but inversely proportional to the wavelength. Short wavelength radiation, such as X-rays, has high frequency, high energy. But low wavelength radiation, such as radio waves, has low frequency and low energy. Sample problem 7.2. A student used a microwave oven to heat a meal. The wavelength of the radiation is 1.2 centimeter. What is the energy of 1 photon of the microwave radiation? So in the last slide, we showed energy is proportional to the frequency, h times nu, or inversely proportional to wavelength, which is h times c divided by lambda. Now, this question tells you the wavelength, so we use this equation. But first, we need to change centimeter to meter. Okay, so plug in the data. So this is Planck constant, is 6.626 times 10 to the minus 34 joule second. Speed of light, which is 3 times 10 to the 8th power meter per second. Wavelength, 1.2 centimeter times the conversion factor, 1 centimeter 10 to the minus 2 meter. So cancel centimeter, give you meter. Okay, so divide by this wavelength, and that gives you 1.66 times 10 to the negative 23 joule. When sunlight passes through a prism, it creates a continuous spectrum or rainbow by refraction. When light from electrically excited gases passes through a prism, it does not create a continuous spectrum. Instead, it creates a line spectrum, a series of fine lines at a specific wavelength or frequencies, separated by black space. For example, hydrogen atoms emit light at around 410, 434, 486, 656 nanometers, separated by black space. Similarly, mercury emit light at around 405, 430, and 545, and so on. So the wavelength of light emitted by atoms are quantized. The Swedish physicist Johan Rydberg developed a mathematical equation called the Rydberg equation to predict the position and wavelength of any line emitted by hydrogen atom. In this equation, lambda is the wavelength emitted by hydrogen atom, and r is a constant, has this value, and n1, n2 are two integers. n1 is smaller than n2. So if n1 is 2, then n2 can be 3 or 4 or 5. Using this equation, you can calculate all the wavelength emitted by hydrogen atom. On the other hand, including Rydberg himself, no one understood what n1, n2 mean, and this has to wait until Bohr model of the hydrogen atom was proposed. Since wavelengths of light emitted by atoms are quantized, the energies of atoms must also be quantized. Niels Bohr proposed that hydrogen atom has only certain energy levels, which Bohr called stationary states. Each state is associated with a fixed circular orbit of the electron around the nucleus. So here is the nucleus and an electron in its orbit, fixed orbit with energy E1. The higher the energy level, the further the orbit is from the nucleus. So you have another fixed orbit with energy E2. So E2 is greater than E1, and so on. When hydrogen electron is in its first orbit, the atom is in its lowest energy state, which is called ground state. The atom does not radiate energy while in one of its stationary state. The atom changes to another stationary state only by absorbing or emitting a photon. So you have a nucleus and you have electron in the ground state, which is E1, and energy state E2, which is called the excited state. So this is the first excited state. And then E3, which is the second excited state. The electron can jump between these energy levels If an electron go from E1 to E2, energy increase. Where does energy come from? It must absorb a photon. In other words, absorb light. The energy of the photon, HV nu, must equal to the energy difference between E1 and E2. So delta E equals to the energy of one photon. Okay, so if electron go from E1 to E2, it absorb energy. If electron go from E2 to E1, it emit light. So emit light with photon energy h nu also equal to the difference between these two energy levels. Here shows quantized energy levels of an atom. The electron of an atom can be in the first energy level, which is called a ground state, or second energy level, which is called the first excited state, or n equals 3, 4, 5, and so on. The electron cannot have energy between these energy levels. Okay, these are the only energy states that are available for the atom. The electron can jump from energy first ground state, from ground state to the first excited state, but it must absorb energy from light, and the light absorbed by the electron must be equal to the energy difference between n equals 1 and n equals 2. Now electron can also jump from n equals 2 to 3, and then it must also absorb light with the energy h nu. In this case, this energy must equal to the delta E between n equals 2 and n equals 3. Okay. Now the electron at the higher energy level, for example n equals 4, can drop to the lower energy level, for example n equals 3. In this case, it must emit light with energy h nu, also equal to the delta E. Okay, or let's say from n equals 3 jump to n equals 1. Okay, and emit a light of h times nu. In this case, it equals to delta E between 3 and 1. Here we use Bohr's model to explain hydrogen spectral lines. According to Bohr's model, hydrogen atom has only certain energy levels of stationary states. So n equals 1, 2, 3, 4, 5, 6. And here also shows energy levels, n equals 1, ground state, and the first excited state, n equals 3, and go on. When gas phase hydrogen is electrically discharged, it becomes excited at high energy. And these high energy electrons are not stable, and they want to go back to the ground state. At the same time, it emits light. For example, at the state n equals 2, go back to ground state, emit light, okay, with wavelength right here. And from 3 to 1, it also emits light with wavelength here. Okay, so these create a series of discrete wavelengths or frequencies. We have introduced the Bohr's model, which says hydrogen atom has a stationary state with fixed energy levels. The energy levels can be n equals 1, n equals 2, n equals 3, nothing between them. Now, the Bohr's work also leads to a very important equation to calculate these allowed energy levels. And this equation is negative 2.18 times 10 to the negative 18 joule times 1 over n squared. This n is the quantum number which defines the energy state. For example, this ground state, n equals 1. So you put n equals 1 here. This is 1, so that's E1. So E1 is this constant times, so constant times 1 divided by 1, okay, because n equals 1. Now for n equals 2, so E2 is this one, which is the constant here times 1 divided by 2 squared. Okay, and E3 should be the constant times 1 divided by 3 squared. So in general, it's the n squared, 1 divided by n squared. So these are the allowed energies for hydrogen atom. Okay, now this equation is very useful. There are many applications. So one application is that we can use this equation to find the difference in energy between two levels. For example, what is the difference between n equals 1 to n equals 2? So if 1 goes to 2, what is the energy difference? Well, we should use the finder, which is E2 minus E1. Okay, and E2 is when n equals 2, so this is 2. And then E1 is when n equals 1. So delta E can be calculated in general by finder minus initial. So in this case, then this is 2 square, and this is 1 square. And you can see that 1 divided by 4 is smaller than 1 divided by 1. So this will be a negative number. And you also have a negative number, and so delta E will be positive. So when energy goes up from 1 to 2, from state 1 to state 2, delta E is positive, means that hydrogen has to absorb energy, and this energy comes from light, so it absorbs a photon to go up energy, okay, from n equals 1, n equals 2, or 2 to 3. On the other side, if n from 3 goes to n equals 1, so in other words, if energy goes down from higher energy level to lower energy level, then final here will be 1, and the initial will be 3 squared. So 1 divided by 1 minus 1 divided by 9, that will be positive. So this gives you a positive number, but you have a negative sign here, so that gives you a negative delta E. Negative delta E means it's released energy. So if hydrogen atom energy goes down from n equals 3 to n equals 1, it must release energy, which release energy as light, emit light as a photon. So it emit photon, light, okay? And we can actually calculate the frequency or wavelength of the photon that emitted by the hydrogen atom. And this leads to the second application. To find the wavelength of a spectrum line, the equation is the delta E. Okay, so the energy change equals the energy of the photon, which is Planck constant times frequency nu. And frequency is calculated by speed of light divided by wavelength. And therefore, wavelength can be calculated by Planck constant times speed of light divided by delta E. Okay, so delta E is the energy difference, for example, from E2 to E3, or E3 to E4, or E4 goes to E1. So you just calculate this difference, okay, and you can calculate the wavelength. Okay, so that's the application 2. Now, application 3 is that we can find the ionization energy of hydrogen atom. Ionization energy is the energy required to remove an electron from the hydrogen atom. So suppose the electron is at the ground state, so it's at the lowest energy level. Now, to remove it, you have to apply energy so that it go to higher energy level, not 2, n equals 2, not 3, but n equals infinity. Okay, that means electron completely out of hydrogen atom. Okay, so n equals 1. Okay, that's the initial state to n final. So if this is initial, is 1, the final is infinity. And the delta E, the energy difference, is 1 divided by infinity. This is 0, minus 1 divided by 1 squared. And that gives you positive 2.18 times 10 to the minus 18 joule. That's the energy difference for one atom, hydrogen atom. Ionization energy of hydrogen atom is defined as the energy to remove electrons from 1 mole of hydrogen atom. And therefore, we need to multiply by Avogadro's number. Okay, that's give you 1 mole of hydrogen atom. And then, so this will change joule or mole, so joule to per mole. Okay, 1 atom to 1 mole. And then we multiply by, divided by 1000. That gives you kilojoule. Okay, so ionization energy of hydrogen atom is 1.31 times 10 to the 3rd power kilojoule per mole of hydrogen atoms. Sample problem 7.3. A hydrogen atom absorbs a photon of UV light and its electron enters n equals 4 energy level. Calculate A, the change in energy of the atom, and B, the wavelength of the absorbed photon. So this question about hydrogen atom that electrons jump from low energy to higher energy. So n equals 4 is the final energy state. Although it doesn't mention the initial n, but implies that initially it should be at the ground state, which is 1. Okay, so the allowed energy is this equation. So that's the constant times 1 divided by n squared. So delta E should be this constant times 1 over n final minus 1 over n initial. So n final is 4. So 4, initial is 1. Okay, so plug in, and we should get 2.04 times 10 to the 18th power joule. All right, so that's the energy difference. Okay, now next one is to calculate the wavelength. So the wavelength of the photon absorbed the energy should equal to delta E. So delta E should equal to the energy of photon, which is Planck constant times frequency. The frequency is calculated by speed of light divided by wavelength. Okay, so Planck constant times speed of light divided by wavelength should equal to delta E. And therefore, the wavelength is Planck constant times speed of light divided by delta E. And delta E just calculated. Here is the Planck constant, and this is the speed of light. So that gives you 9.74 times 10 to the minus 8. Note the unit is meter. The question asks in nanometer, and therefore we multiply conversion factor. 1 nanometer, 10 to the negative 9 meter. So cancel meter, give you nanometer, which is 97.4. When an electron inside an atom is excited to a higher energy level, it may go down to a lower energy level by emitting light. The wavelength of the emitted light depends on the energy difference, and this energy difference depends on the identity of the atom. So by measuring the wavelength, we may find the identity of the atom, and the flame test is one of these chemical analysis. So flame test is performed by placing a small amount of sample inside the flame. The atoms inside the sample is excited due to the heat inside the flame, and the excited atoms emit light of different color. For example, strontium emit red light, copper emit blue-green light, and sodium emit orange light. Fireworks display emission similar to those seen in flame test. Similar to the flame test, but more accurately, we can measure the wavelength of emitted light by using an instrument called emission spectrometer. and the spectrum is called emission spectrum. The opposite of this emission spectrum is called absorption spectrum, which is produced when atoms absorb a photon of a certain wavelength and become excited. For the same atom, the bright emission lines are the same as the dark absorption lines. And this is because both are created by the same energy change. Here shows a typical spectrometer, which starts with a source that generates light with many wavelengths. This light goes through a lens, a monochromator, becomes a single wavelength, and this light passes through a sample. If the orbital energy difference of the atom inside the sample holder equals the energy of this light, which is Planck constant speed of light divided by the wavelength, then this light will be absorbed. If these two doesn't equal, then this light pass through sample goes to the detector. By scanning a range of wavelengths, the instrument can find the wavelengths that can be absorbed by the sample. We have shown that light has wave properties, including refraction, diffraction, and interference. The blackbody radiation and other experiments showed that light also have particle properties. The energy of light is h nu, 2h nu, 3h nu. It's like particles. The energy is quantized. All these suggest that light is a wave but also a particle. It has wave-particle duality. A French physicist, de Broglie, proposed that all matter, not just light, all matter exhibit properties of both particle and wave. And electrons are believed to be particles, but the electrons also behave as wave, and therefore have only certain allowed frequency and energies. De Broglie further derived a mathematical equation to calculate the wave of any particle. So if a particle has a momentum, which is m times velocity, speed, so mass times speed, that's the momentum of the particle, then the particle also behaves as a wave with wavelength calculated to be Planck constant divided by the momentum. So Planck constant divided by momentum, and the wavelength is called de Broglie wavelength. According to this equation for the de Broglie wavelength, matter behaves as if it moves in a wave. An object's wavelength is inversely proportional to its mass. So heavy objects, such as Earth, baseball, with large mass, the calculated wavelength can be so small compared to the size of the objects themselves that they cannot be detected. On the other hand, for smaller particles, such as electrons, the calculated wavelength can be as the same size as electron itself. And so for electrons, the wave property is very important. Sample problem 7.4. Find the de Broglie wavelength of an electron with a speed 1 × 10⁶ meter per second. So the equation of de Broglie wavelength is Planck constant divided by momentum, and the momentum is calculated by mass times speed. So the mass is given here, 9.11 × 10⁻31 kilogram. Note that SI unit is kilogram for mass, all right? And speed is 10⁶. So plug in the data. The Planck constant is this number. The unit usually is joule second, which is also equivalent to kilogram meter squared per second. Okay, so divided by mass, divided by speed, and that gives you 7.27 times 10 to the minus 10 meter. The postulate that all matter exhibit particle-wave duality has been confirmed by countless experiments. Here shows the diffraction patterns of aluminum with X-rays and electrons, and this clearly shows that the X-ray and the electron both have wave properties. The wave property of electrons has been utilized to make an electron microscope. Here is an image of blood cell taken by scanning electron microscope. If a particle, such as an electron, also have wave properties, can we determine its position? A German physicist postulates that it is impossible to know simultaneously the position and the momentum of a moving particle at the same time. The mathematical equation for this Heisenberg uncertainty principle is that delta x, okay, x is the position, so delta x is the position change or the uncertainty of position. Delta u is the uncertainty of the speed, so times mass, and this is the uncertainty of momentum. So the uncertainty of position, uncertainty of momentum, the product is greater than a small number, which is the Planck constant divided by 4 pi. Now suppose delta u approach 0. So if delta u approach 0, that means the speed doesn't change. That means we know speed. So when delta u approach 0, we know quite accurately about the speed. Then what happens to x position? Well, because the product is greater than this number, so if one approaches 0, the other must increase. So that means we have a large uncertainty of position. In other words, the more accurately we know the speed, the less accurately we know the position, or vice versa. Sample problem 7.5. An electron moving near an atomic nucleus has a speed 6 times 10 to the 6th power meter per second, plus minus 1%. Okay, note that this is the uncertainty. What is the uncertainty in the position delta x? So for speed u, this uncertainty 1% we need to calculate first. So we calculate the uncertainty is 1%, which is 0.01, times 6 times 10 to the 6th power meter per second. So this is the uncertainty of the speed delta u. According to Heisenberg uncertainty principle, delta x times m times delta u, so this is the momentum uncertainty, is greater than h over 4 pi. So we can calculate delta x, which is h divided by 4 pi divided by m divided by delta u. Okay, so plugging everything, and this is Planck constant, 4 pi, mass, and delta u, and that gives you 10 to the negative 9th power meter. All right, so that's the uncertainty in position. Although this delta x is a small number, this is actually 10 times greater than the diameter of a whole atom, and therefore we have no idea where the electron is inside an atom. You have learned that at atomic scale, particles also behave as a wave. Now, Bohr's model was very successful about hydrogen atom. However, it does not include the wave nature of electrons, and therefore we need a new theory to describe atoms. And the new theory is called quantum mechanics. Quantum mechanics examines the wave nature of objects on the atomic scale, and this theory is based on a mathematical equation called Schrödinger equation. In this equation, this is called the Hamiltonian operator. In mathematics, there are many operators. For example, 5 times 6. We can think 5 times as an operator and simplify this operation as operator operates on 6. And because this operator refers to 5 times, so when this operator operates on 6, that gives you 30. Okay? Of course, Hamiltonian operator is more complex. And in this equation, E is the energy of the system, and the psi is similar to the variable x or y, but for hydrogen atom, it's called orbital. Okay, and therefore, when you solve Schrödinger equation, you get the solutions, and each solution of the equation gives you an energy state, which is E, associated with a given atomic orbital, which is psi. Now, in Bohr's model postulates that the hydrogen atom has stationary states. The electron is in its orbits with fixed radius. Due to the wave nature in quantum mechanics, psi, or the atomic orbital, does not have fixed radius. In fact, it's just a mathematical equation to describe the atomic orbital. And even though it's a mathematical equation, it does not have physical meaning. But when you square it, so you get psi, okay? It's a mathematical description. When you square this mathematical equation, you get the probability density. So square it have a physical meaning. That's the probability density of the electron, which is a measure of the probability of finding an electron of a particular energy in particular region of the atom. So in essence, by solving Schrödinger equation, you find the energy of the hydrogen atom, and you find the probability density of the electron in space. Here shows different ways to describe electron probability location. So by solving Schrödinger equation, we find psi, and we square it and plot a psi square as a function of distance. Closer to the nucleus, when distance is very small, we find very high probability density. When distance increases from nucleus, the probability density decreases. Okay, here in this diagram, we use dots to represent psi squared. The greater the density of dots, the higher the probability of finding the electron in that volume. So again, we see that greater density of dots close to nucleus, and that means high probability density there. Now this diagram is called radial probability distribution plot. So we first mentally divide the volume around the nucleus into thin, concentric, spherical layers, like the layers of an onion. And then we find the sum of psi squared. So sum of psi squared values in each layer to see which is most likely to contain the electron. So close to the nucleus, okay, we have very high psi squared, but the volume is so small. Okay, the sum of psi squared is very small number. When increase distance, okay, you get a layer volume increase. Okay, so the sum of psi squared increase. But at very high distance, even though the volume becomes very large, but the psi squared becomes too small. And so the sum of psi squared also decrease. And so you have a peak here, okay, at this distance. Okay, this is called the most probable distance. You will find the highest sum of psi squared at a layer that at this distance of the layer at this distance. Okay. Now this diagram is called 90% probability contour. So the electron is somewhat within this volume 90% of the time, and this also give you relative size of the atom. In the following, I'm going to present the major results from Schrödinger equation of a hydrogen atom. An atomic orbital is specified by 3 quantum numbers. Remember, when we solve Schrödinger equation, we get energy and psi. And psi is a mathematical description of the atomic orbital. Each psi contains 3 quantum numbers, n, l, and m. So these quantum numbers are included in each of psi of the mathematical equation. N is called principal quantum number. Okay, it's an integer, positive integer. For example, it can be 1 or 2 or 3 and so on. The value of n indicates the relative size of the orbital, and therefore it is the relative distance from the nucleus. And the number also specifies the energy level of hydrogen atom. So in this sense, this n is similar to that in Bohr's model. However, in Bohr's model, each orbital has a fixed radius. And due to the wave nature, this is not true here. Psi does not have a fixed radius, but it has a very average distance. So, or the most probable distance. So, for example, when n equals 1, the most probable distance is smaller than the most probable distance when n equals 2. Okay, so it's closer. In this sense, it's relatively closer than n equals 2. Okay, the most probable distance for n equals 2 is smaller than that when n equals 3. So n equals 2 is closer, relatively closer than n equals 3. The second quantum number is L, called angular momentum quantum number, because this quantum number determines the angular momentum of the orbital. This angular momentum quantum number is also determined by quantum number n. So for example, when n equals 1, L can only be 0. When n equals 2, L can be 0, 1, that's it. The maximum is n minus 1. So from 0 to n minus 1. The maximum is n minus 1. Okay, L also indicates the shape of the orbital. In chemistry, we have a name for each of these L. For example, when L equals 0, we call it s orbital. When L equals 1, we call p orbital. When L equals 2, we call d orbital. And when L equals 3, we call it f orbital. The magnetic quantum number m is an integer that is determined by L. So for example, when L equals 1, m can be negative 1, 0, positive 1. Okay, 3 of them. When L equals 2, okay, the possible m can be negative 2, negative 1, 0, positive 1, positive 2. So in general, it's from negative L to positive L. Magnetic quantum number also indicates the spatial orientation of the orbital. For example, when L equals 0, m can only be 0, right? Because maximum is L. So from negative L to positive L. So when L equals 0, m can only be 0. And so there's no orientation. In fact, it's a spherical. This orbital is a spherical. When L equals 1, okay, here we call p orbital. The possible m can be negative 1, 0, positive 1. So there are 3 orientations, and these are px, the orbital along x direction, py along y direction, pz along z direction. Let's summarize the quantum numbers for hydrogen atomic orbitals. Principal quantum number n determines the energy of the system and gives you the relative size of the orbital. The possible values are positive integers, 1, 2, 3, and so on. The angular momentum quantum number, L, determines the angular momentum of the orbital and also tells you the shape of the orbital. The possible values are determined by quantum number n, so from 0 until n minus 1. For example, when principal quantum number is 1, the only value is 0. Okay, when quantum number n is 2, it can be 0 to 1. When principal quantum number is 3, the value can be 0, 1, and 2. Magnetic quantum number m determines the orientation of the orbital, and the value is determined by quantum number L. So it can be negative L until positive L. For example, when L equals 0, m can only be 0. When L is 1, m can be negative 1, 0, positive 1. When L equals 2, okay, when L equals 2, m can be negative 2, negative 1, 0, positive 1, positive 2. The name for L, okay, when L equals 0, and this is called the s orbital, okay, and s orbital has zero orientation, no orientation. So m also tells you the orientation of the orbital. This is 1s, and this one is 2s orbital. Okay, principal quantum number 2 is a s orbital. All right, and this is a 2p orbital with 3 orientations. Okay, 2px, 2py, 2pz. When n equals 3, we have 3s orbital and 3p orbital. You have 3 orientations and 3d orbital. Okay, when L equals 2, that's d orbital, and it's a 3d orbital with 5 orientations. Sample problem 7.6. What values of angular momentum quantum number L and magnetic quantum number m are allowed for a principal quantum number n equals 3, and how many orbitals are there in this energy level? Okay, so we know that L is determined by n, so from 0 until n minus 1, and m is determined by L, and it can be negative L, 0 until positive L. Okay, so when n equals 3, so L can be 0, 1 until n minus 1, which is 2 in this case. Okay, remember this is called the s orbital, this is called the p orbital, and this is called the d orbital. So more precisely, it's 3s orbital, 3p orbital, and 3d orbital. When L equals 0, that's for s orbital, the L can only be 0. So we have L equals 0, m is 0. So that's this one, it's 3s orbital. Okay, when L equals 1, we can have m can be negative 1, 0, positive 1. So that's 3p orbital. You have 3 orientations. Okay, 3x, 3y, 3p. So 3 of the d orbital or p orbitals. When L equals 2, we can have m can be negative 2, negative 1, 0, positive 1, positive 2. So that's for d orbital. We have 5 of them. Okay, 5 orientations. All right. So when n equals 3, the total number of orbitals is, okay, 1 is for s orbital, 3 for p orbital, and 5 for d orbital. So the total is 9. So 9 orbitals. Okay, in general, the total number of orbitals for a quantum number n is n squared. So when n equals 3, 3 squared is 9. So total is 9 orbitals. When n equals 2, 2 squared is 4. So the total is 4 orbitals, and that's 2s orbital and 2p orbital. So remember, you have 3 of them, 3 2p orbital plus 1 s orbital, and that's 4. Sample problem 7.7. Give the name, magnetic quantum numbers, and the number of orbitals for each sublevel with the following quantum numbers. Okay, we need to combine n and l to name the sublevel, and knowing L, we can find M and the number of orbitals. For example, the first one, L equals 2, and that is the d orbital. And because n equals 3, so it's called the 3d orbital. And what are the values of M? M is determined by L. When L equals 2, it can be -2, so -2, -1, 0, +1, +2. Okay, so for A, here is the answer. N is 3, L is 2, and it's called a 3d orbital, and the possible values are -2, -1, 0, 1, 2, and there are total of 5 number of orbitals. Okay, next one, L equals 0, that's a s orbital, n equals 2, so 2s orbital, and the possible value for m is only 0, so you only have 1 orbital. Okay, so that's 2s orbital. Next one, L equals 1, so that's a p orbital, and it's a 5, so 5p orbital, and the possible orientation, okay, for m is -1, 0, +1, so you have 3 possible values, and you have the number of orbitals is 3. Okay, next one, L equals 3, that's a f orbital, and it's a 4f orbital, and the possible values for m is -3, -2, -1, 0, +1, +2, +3. So that total number of possible m is 7. So that is 7 number of orbitals. Sample problem 7.8. What is wrong with each of the following quantum numbers, designations, and or sublevel names? Okay, let's look at A. N equals 1. Principal number is 1. L can be 0 until n minus 1. So when n equals 1, 1 minus 1 is 0. So 0 is the only value for A. So 1 is not one of the possible values for L. So this is wrong. Okay. Second one, okay, let's look at B. When n equals 4, so L can be 0, 1, 2, until 4 minus 1, 3. So that's all the values L can be. And 3 is one of them, so that's correct. And when L equals 3, it's called the f orbital. So it should be 4f. And this is wrong. Okay, the name is wrong. Next one, when n equals 3, L can be 0, 1, 2, and that's it, because 3 minus 1 is 2, so 2 is the maximum. And 1 is one of the possible values, so that's correct. And when L equals 1, it should call the p orbital, so it's 3p orbital, and that's all right. And when L equals 1, what are the possible values for m? M can be -1, 0, +1. Okay, and -2 is not one of them, so this is wrong. Okay, so so number C, the value of m is not right. Here shows the shape of the wave function when L equals 0. which include 1s orbital, 2s orbital, and 3s orbitals. And this is a plot of psi squared as a function of distance, or the probability density as a function of distance. And you can see that all these wave functions or orbitals, the closer to the nucleus, the higher the probability density, higher probability density. Now remember, when it's closer to the nucleus, the volume becomes very small, and therefore the probability to find the electron close to the nucleus is actually very small because of the small volume. So another way to look at it is here, the plot called the probability distribution function, okay? Radial probability distribution. And imagine the atom consists of layers of structures like onion, and we find the sum of psi squared inside each layer and find the probability, okay? And you can see for 1s orbital, there is a distance, okay, where the probability is the maximum in that layer, okay? So this is the most probable distance for 1s orbital. For 2s orbital, we found two maximums, and the second one is the largest, is larger, okay? And you can see the distance here, okay, is greater than the distance of the maximum for the first one, 1s orbital, okay? And that means, in average, the electron in 2s orbital is further away from nucleus than 1s orbital. Similarly, for 3s orbital, okay, we see 3 maximum, and the largest maximum has a distance further away to the nucleus than 2s orbital. Okay, so for 3s orbital, electron is even further away from nucleus than 2s orbital. We also find that for 2s orbital, there is a distance where the probability is 0. So in that layer, there's no probability to find the electron, and this is called a node. Okay, so probability becomes 0. And in 3s orbital, we find 2 of them, okay, where probability to find the electron is 0. Now this is called 90% contour, okay, probability, 95% probability contour, okay? And you can see 2s orbital is larger than 1s, and the 3s orbital is even larger. And you also see here, you have a white layer, okay, which represents this node where probability is 0, okay? And in 3s orbital, we see 2 layers, okay, 1 and 2, where the probability to find electrons are zeros. This diagram shows the shape of 2p orbital where L equals 1. And here is the radial probability distribution. The most probable distance is longer than that in 2s orbital. So the electron in 2p orbital is in average further away from nucleus than the electron in 2s orbital. And this is an accurate probability contour. And this shows that each orbital contains 2 regions called lobes. Okay, the electron spend equal time in both lobes. For this particular orbital, the highest probability density of the electron is along z direction and the negative z direction. And that's why this orbital is called 2pz. Also notice that there's no probability to find the electron on this plane. Here is the xy plane, so no electron probability along this direction or the plane. So this is called a nodal plane. Okay, when L equals 1, okay, we know that M can be -1, 0, +1. So there are 3 orientations, and z direction is one orientation, this one. Okay, there are 2 other orientations. So here shows all the 3 orientations, and this is pz, okay, And the second one is an orbital along x direction called a px. Also, you see two lobes. And here, the third one is py. There are two lobes also. Okay. Now, this is a stylized probability contour that clearly shows the double dumbbell shape that commonly seen in textbooks. This shows the shape of 3D orbital where L equals 2. And this is the radial probability distribution with the most probable distance here. And this is the accurate probability contour. And you can see this orbital contains 4 lobes. Okay, 1, 2, 3, 4. And one of them is between x and y axes. And so this is called a 3D YZ orbital. Okay. Also notice that there are two nodal planes. Okay, so nodal planes. So one is this one, where there's no electron probability to find the electron, and there's another one here. Okay, so for this orbital 3D YZ, the nodal planes are xz, okay, plane xz and plane xy. Okay, now this is the stylized probability contour of 3D YZ. For L equals 2, we already know this should have 5 orientations because M can be -2, -1, okay, 0, 1, and 2. So 5 orientation. So this is only one orientation, and there are 4 more, and that is 3D xz, 3D xy, and 3D x squared minus y squared, and 3D z squared. So put them all together, and that's the diagram for 5 3D orbitals. When L equals 3, the orbital is called F orbital. And when L equals 3, there are 7 M possible orientations. And this diagram shows one of the 7 orbitals called 7fxyz. This table summarizes the quantum numbers n, l, m, the names of the orbitals, and the number of the orbitals. So n can be 1, 2, 3, 4, so positive integers. L is determined by n, can be 0, 1, until n minus 1. Okay, so for n equals 1, L can only be 0. Okay, so the sublevel means this one, L. Okay, when L equals 0, it's called S orbital. So in this case, it's 1s orbital. And M is determined by L. So it can be -L, okay, 0 until positive L. So if L equals 0, then the only value is 0. The number of orbitals in sublevel means that how many, so this is sublevel, it's 1s. The question is how many orbitals for 1s orbital? That's sublevel. So in this case, it's just 1. In general, it's 2L plus 1. So 2 times 0, because in this case, L is 0. So 2 times 0 plus 1, that's only 1. 1s orbital, only 1 orbital. And the total number of orbital is n squared. So that's determined by n. So when n equals 1, n 1 squared is 1. Just 1s orbital. So when n equals 1, the total number of orbital is 1, 1s orbital. Now let's look at the 3. So when n equals 3, L, okay, according to this one, you can have 0, 1, and 2. Okay, and the name for L equals 0 is called s orbital, because n is 3, so 3s orbital. When L equals 1, it's called 3p orbital. When L equals 2, it's called 3d orbital. All right, and M is determined by L. So when L equals 0, M can only be 0. All right, when L equals 1, so that 1 is 3p orbital, then M can be -1, 0, +1. All right, so for this subshell, that's 3p orbital. How many of them? Okay, according to this equation, 2L plus 1. When L equals 1, 2 times 1 plus 1 is 3. And that's -1, 0, +1. When L equals 2, the possible value for M is -2, -1, 0, +1, +2. Total is 5. And according to this equation, 2L plus 1, 2 times 2 plus 1, that's 5. Okay, so that's the number of orbitals in sublevel. Okay, in this case, is how many orbitals in 3D, and that's 5. Okay, now what is the total number of orbitals in energy level 3, n equals 3? Well, that's n squared. 3 squared is 9. This diagram shows the energy levels of hydrogen atom. The energy of hydrogen atom depend only on n value, the principal quantum number. So the lowest energy, or the ground state, is 1s orbital. N equals 1. L can only be 0. M can only be 0. And so you only have one orbital, and that's 1s orbital. When n equals 2, L can be 0, and that's 2s orbital, and L can be 1, and that's 2p orbital. And we have 3 of them. So in total, we have 4 orbitals. Okay, it's 2 squared, n squared. Okay, so 4 orbitals. These 4 orbitals have the same energy because they all have principal quantum number 2. The principal quantum number is the same, and the energy only depends on n. Similarly, when n equals 3, we have 3s orbital, 3p orbital, 3d orbital. In total, we have 3 squared, which is 9 orbitals. And these 9 orbitals have the same energy because the principal quantum number is the same, 3. Okay? Now I want to mention that this result is only true for hydrogen atom. Now later, when we talk about multi-electron systems, such as helium, neon, that atom has more electrons, then the energy levels looks different. Okay, so 1s orbital is still the ground state, lowest energy state, and then you will come to 2s orbital, and then 2p orbital is slightly higher than 2p orbital, 2s orbital, and then you have 3s orbital. Okay, so 3s orbital here, and then 3p is higher, and then 3d orbital even higher. So those are for multi-electron system. But for hydrogen atom, the energy only depends on principal number n. And when n equals 2, 4 orbitals are all the same energy. Okay, so these are called degenerate. When different orbitals have the same energy, they are called degenerate. Okay, this is true for hydrogen atom here.